Hello everyone, welcome back to my channel Physics 4AP. So in previous episode we were discussing about the classification of elements, that we have discussed about the Dobinid law of triads. So on that we have discussed about the law of triads, and next we have discussed about the Newland law of octaves, and we have discussed about the successful and also the limitations which were faced by the Dobinid and the Lewis. So now today we are going to discuss about the Mendeleef periodic table. So the Mendeleef periodic table, the scientist name called the Mendeleef have designed this periodic table. Now today whatever the modern periodic table we are having, so that is the main basics which is given by the Mendeleef periodic table. That is, most of the elements has been covered during that 18th century, during the 18th and 19th century. So the Mendeleef was very successful to arrange the elements in its periodic table. So what coming to his law is that the physical and the chemical properties of the elements are a periodic function of their atomic weights. That is, he has arranged the elements according to the basis of their atomic weights. That is, he has been arranged them in the increasing order of their atomic weights, and also based upon the physical and the chemical properties he has arranged them in a groups and periods. As if we see the silent features over here, the silent features and achievements. So first he has divided into groups, and in that groups he has divided into subgroups. So in his Mendeleef periodic table, so here we have 8 vertical columns. So those 8 vertical columns are said to be called as groups, and they are represented by the Roman numerals, which are Roman 1 to Roman 8. That is Roman 1, 2, 3, 4, 5, 6, 7, 8. And next, and each group is been divided into a subgroup which we called as subgroup A and subgroup B, like 1A, 1B, 2A, 2B, 3A, 3B. So like that he has divided into a subgroups, and he said that the elements which are present in the groups, that is the elements which are present in a groups, have the same physical and chemical properties. Like example, if we take 1A, first group, and in that we have two subgroups, subgroup A and subgroup B, and at the same time second group, so we have subgroup A and subgroup B. So what I was saying is, the group which we have in the first group, either A or B, all have the same physical and the chemical properties. So the subgroup 2, so all they have the physical and the chemical properties. So this is what the Mendeleef periodic has explained about the groups and the subgroups. Now coming to the periods, in periods he has 7 horizontal rows. So the horizontal rows, which are 7, they are called as the periods. So the horizontal rows, so which we call the horizontal rows, are said to be called as the periods, and they are represented by the Arabic numerals like 1 to 7. So represented by 1 to 7 the Arabic numericals, and their properties are dissimilar. So the property there which we are going along the group from left to right, so the properties are dissimilar, that is the properties are different. Now another silent feature, that is, he predicted the properties of the missing elements. So in Newland periodic table, as he didn't left any space, and he didn't predict any new elements, but Mendeleef has predicted some missing elements, and also he has left blanks for the future elements, that is for the upcoming elements which are going to come. He has left the blanks in his periodic table to place it there, and also he has predicted some of the missing elements, as the elements were not discovered at that time, but he has predicted the physical and chemical properties of the elements. He had named them the 3 elements like as Eka boron, Eka aluminum, Eka silicon. So Eka means, it is a Sanskrit word which means called one, that means only one. So as Eka boron and Eka aluminum, Eka silicon, the physical and the chemical properties were further predicted by Mendeleef, and he had named the Eka boron, Eka aluminum, Eka silicon, and he had placed a place in his periodic table and given the atomic weights, the chemical reaction with the oxygen and halogens and others, and he had predicted that these elements which are going to come further later on, when coming to the modern period, after few years later, so the new elements were discovered at that time, that the scandium, gallium and germanium. After finding the chemical properties and the physical properties of this scandium, gallium and germanium, so these were quite similar to the elements which were protected by Mendeleev, that is Eka boron, which were protected on that time. So those properties which was given by Mendeleev was same as equals to the properties of the scandium. Now, so here in the place of Eka boron, the scandium has been replaced, and at the same time of Eka aluminum. So Eka aluminum, the properties which were predicted were quite similar to the gallium. Now in the place of Eka aluminum, gallium was being replaced. At the same time, Eka silicon, so the properties were similar to that of germanium. So in the place of Eka silicon, so germanium was being replaced. So he predicted the future elements which were upcoming elements, and also he had predicted the properties of those elements, and he was successfully done with it. Next, one of the silent features, which is the correction of the atomic weights. So as a correction of atomic weights, so at that time what we discussed in Dobbin and Newland, the atomic weights were not accurate at that time, but the Mendeleev had given a formula, that is the atomic weight is equals equivalent weight into valency. And as the beryllium, like example, if we take the beryllium, so beryllium atomic weight was 13.5 units, that is in before the Mendeleev periodic table, but that beryllium atomic weight was quite wrong. Why? Because at that time the beryllium valency was given as 3, but actually the beryllium valency is not 3, its valency is 2. By the given formula over here, so atomic weight is equals to equivalent weight, that is 4.5 of the beryllium into the valence of the beryllium is 2. Now if we multiply these two, we get 9. Now 9 is the correct atomic weight of the beryllium. So at that time he had corrected the valencies of the elements. As the beryllium valency was 3, he has corrected it as 2 and given the correct accurate atomic weight for the beryllium. And also he has also corrected the atomic weights for the indium and gold. For the indium and gold also he has corrected, not only indium and gold, some other elements also they were there which has been corrected by the Mendeleev, and they were placed in a correct position in the Mendeleev periodic table. Now coming to the another silent feature, which is the anomalous series. So anomalous series is nothing but which is mean by no explanation. Like if we see here tellurium and iodine. So tellurium atomic weight is 127.6 U and iodine weight is 126.9. Actually, as this Mendeleev periodic table is based upon the atomic weight, it should be arranged with the increasing order, right? So that means first we should get the iodine, which is 126.9, and then we should get the tellurium, which is 127.6. So actually this is the correct way that according to this periodic table. So first we should get the iodine and then we should get the tellurium according to the increasing order of their atomic weights. But Mendeleev has done that, he has corrected the groups. Like what he has done is he has replaced the tellurium and iodine. As he has replaced that, the physical and chemical properties were same what was being corrected into that group. Like before, iodine and tellurium were kept in this way. So the physical and chemical properties along the group, that is the elements which is present in this group, was quite different when compared to iodine, as same as for tellurium also. Now what he has done, he just replaced these two elements, like first the tellurium and then iodine. Then the chemical properties and the physical properties along the group has been successfully arranged. So he has arranged these type of elements, that keeping the higher element before and the lower element after, and arranged them in a correct groups. So this is one of the silent features of the Mendeleev periodic table. Now coming to the limitations, as what are the limitations is that the first we say the anomalous space. So anomalous space, as this periodic table should be arranged according to the increasing order of their atomic weight. But here arranged the highest atomic weight of element has been placed before the lower atomic weight. Like first he has placed tellurium and then he has placed iodine. So this was the one of the failure, as it was a success set, but it has been a failure. Why? Because it should be arranged according to the increasing order of their atomic weight, so which has been violated the periodic law. Now next, coming to the dissimilar elements, he has placed it together. Now coming to the dissimilar elements has placed together, like if, as I told you before, the first group or the 8th group or 7th group, whatever made, the group properties should be same. Like if we see here, the first group, as if we see, we have the subgroup 1A and 1B. So in 1A we have the lithium, sodium, potassium, which are alkali metals, and 1B which have copper, silver and gold, which are called as coinage metals. So as they are the metals, but in further some of the groups, like if we take the 7th group, in the 7th group we have 7th A, so we have chlorine, and 7th B we have manganese. But here in a 7th group, the 7th A, which is chlorine, is a non-metal, and 7th B, manganese, which is a metal, which has been violated the law. So that is, he has placed the dissimilar elements together over here. So that is, in a 7th grade, that means it should be a metal or it should be a non-metal. But in the case of subgroups over here, in subgroup A it has been taken as a non-metal, the subgroup B it has been taken as a metal. So this is the complete explanation of the Mendeleev periodic table. So in Mendeleev, so he has placed it according to the atomic weights. So the successful features, that is the groups and subgroups, he has 8 vertical columns and noted with the Arabic numerals with the subgroup A and subgroup B. And we have the periods, 7 horizontal periods, which are represented by the Arabic numericals 1 to 7. And he has predicted some of the properties of the missing elements, like these what we had discussed before, the Eka boron, Eka aluminum, Eka silicon. So these properties were discussed before. And next he has corrected the atomic weights of the elements at that time, like he has corrected for beryllium, he has corrected for indium, gold. And next the anomalous series, arranging the higher element first and the lower element next, and has been corrected in a group. So coming to the limitations, that is the anomalous space, which has been violated the periodic law. And next the dissimilar elements, which has been placed together as subgroup A, which is the non-metal, and here the subgroup B, which is the metal, which has been violated the law with the periodic law. So almost he was being successful of placing the elements in the periodic table. So on his success, so he has some of the scientists had named the 101 element. So Mendeleev, on the success of the Mendeleev, on his honor, so 101th element was named as the Mendeleevium, so due to his success. Now we will be seeing the periodic table of the Mendeleev's periodic table that you will be seeing now. So this is the Mendeleev periodic table. So as if we see, there are left blanks over here for the future elements, and this is almost the most successful periodic table. Now next, coming to the next periodic table, which is the modern periodic table. So the modern periodic table, the table which we are using now in this century, that is the modern periodic table. So this modern periodic table was designed in the early first of the 20th century. So which was designed by H.J. Moseley. So Henry J. Moseley, which was designed by him. So how he has designed this modern periodic table is, he has analyzed the X-ray patterns. That is, when an X-ray pattern has been sent to a certain elements, so the number of positive charges can be counted out. So based upon the number of the positive charges, so he's taken that the total number of the positive charges which are present in an atom is taken as the atomic number. Now in modern periodic table, so based upon the analysis of the X-ray patterns, he has arranged the elements in a correct order. So he has arranged the modern periodic table not with the atomic weights but with the atomic numbers. So the same mistake which was common by the Daubeney, Newland and Mendeleev, the three same mistakes what they have taken is they have taken with the atomic weights. So that mistake he has been analyzed and he has done with a separate experiment called the X-ray patterns, and find out the positive charges in atom and taken it as the atomic number of each and every element. So the law of the modern periodic table can be considered as the physical and the chemical properties of the element are the periodic function of the electronic configuration. So in the place of electronic configuration, we can take it as the atomic number also. So in the place of electronic configuration, we taken as atomic number. So but electronic configuration is nothing but based upon the atomic number only we consider the electronic configuration, right? So this is about the modern periodic law, which was discovered by which was designed by H.J. Moseley with the help of the X-ray pattern analysis. And coming to the groups and periods, so how many groups are here? We can see there are 18 vertical columns. So 18 vertical columns are present, so which are called as the groups, and they are represented by the Roman numericals, that is from Roman 1 to Roman 8, along with the subgroups as A and B. And next, coming to the groups, what we have here is, like if we take the 1A, 2A, 3A, 1A, 2A, 3A, 4A, 5A, 6A, 7A and 8A. So these are the groups, and each group has a particular name, that is they have a family, the particular family, what we call as the 1A, which is called as the alkali metal family, and the 2A, which is called the alkali earth metal family, and 3A is called the boron family. The 4th A, which starts with the carbon, so it is called as the carbon family, and the 5th A, which is called the nitrogen family, or we can call it as the nitrogen family also. So the 6th A, which is called as the chalcogen family, or we can call it as the oxygen family also, and the 7th A, which is called the halogen family, and the 8th A, which is called as the noble gas family, or which we call the inert gases. Now coming to the valency shell electronic configuration, so what will be the basic electronic configuration for this is, so for 1A we get the electronic configuration as NS1. So NS1, so N bit can be taken as any like shells, like 1 shell or 2 shell, 3 shell, and so on, what it may be. So NS1. Coming to the 2A, so 2A is said to be called as alkali earth metal family. So alkali earth metal family, we can write it as NS2. And next, coming to the 3rd A, that is the boron family, we can write it as NS2 NP1. Now coming to the 4th A carbon family, we can write it as NS2 NP2. And coming to the nitrogen family, we can write it as NS2 NP3. And chalcogen family, NS2 NP4. And halogen family, we can write as NS2 NP5. And coming to noble gas, NS2 NP6. So this is the general valency shell configuration for these groups. Now coming to the valency electrons and valency, what is the valency electrons and what is the valency, that we'll be seeing later. Okay, now coming to the periods, so periods we have same as usual for the Mendeleef periodic table. So there are 7 horizontal rows which are called as periods, and these 7 horizontal rows, that is the periods, which are called as the shells, or which we call the orbits over here. Now coming to the general representation of a periodic table, of a modern periodic table, if we see here, now this is the modern periodic table which we have. So this is the first E group, which are called the alkali metal family, and the second A group, which are called as alkali earth metal family, and coming to the 3rd A, which is called as the boron family. From here and so on, we get the 8th A, which is called the inert gases, or the noble gases, which we call here. Clear? Now in this modern periodic table, so it has been divided into 4 groups, like what we have the SPDF orbitals. So S orbital family, P orbital, and D orbital, and F orbital. So what that can be considered is here we have the first A and the second A. The first A and second A, these 2 blocks, that is these 2 groups, belongs to the S block element. So as they have S in their outermost orbit, that is while writing the electronic configuration last, they have S at their last, so these comes under the S block elements. Now coming to 3rd A to 8th A, so the whole thing, the elements which are coming over here are the P block elements. Why? When we write the electronic configuration, we get lost as P over here, so it is said to be called as the P block elements. And coming to the middle, which we have the B groups, that is starting from 3A, 3B, 4B, 5B, 6B, 7B, 8B, and 1B and 2B. So this is said to be called as the D block elements. So these are said to be called as the D block elements, or which we call it as, we have the another name which is called as the transition element. So we call them as the transition elements. And next, coming to the F block elements. So these two which are represented under the below of the modern periodic table, which are called as the F block elements. So which are also called as the inner transition elements. So these are called as the inner transition elements. Now here if we see the two F block elements, which are called, the first one is called the lanthanides, which starts from cesium, selenium to lutetium, which is the F block elements, which belongs to 4F. These all electronic configuration starts from end to 4F. And coming to the anthanides are starting from thorium to lawrencium. So these end with the electronic configuration of 5F. So in competitive examinations they may ask the name, the group of the what is called the element which ends with the 4F. So which are called as F block elements, but they are said to be called as lanthanides. Which elements are end with the 5F elements, which are called as the actinides over here. And the F block are also called as the inner transition elements. So this is about the modern periodic table, the S block, this is the P block, this is the D block, and this is the F block. Now coming to the valency electrons and valencies. So valency electrons are nothing but the electrons which are present in the outermost orbit. So which are present in the outermost. How many electrons are present in the outermost orbit is said to be called as valency electrons, and the combining capacity of the element is called as the valency. That is, if we take two elements and these two elements need to combine together to form a compound, so the combining capacity of these two elements, which we call them as the valency. So we'll be having an episode upon this also. Now if we take an example of valency electrons, as valency electrons we can take an example for magnesium. So magnesium, which is the atomic number, is 12. So when we write the electronic configuration, so while you're learning the chemistry, the most important thing that you need to learn is the electronic configuration. Without electronic configuration, you cannot solve the mysteries in the chemistry. So magnesium, we have 1s2, 2s2, 2p6, 3s2. Now if you see here the number of electrons, if you count the number of electrons, we get 12, right? Now which is the outermost orbit? So as if you see here, 1s, which belongs to the first orbit, that is K shell, and 2s and 2p, these are the second orbit, which is the L shell, and 3s, which is the third orbit, which belongs to M. Now what is the number of electrons which are present in the third orbit? So in third orbit we have the number of electrons, which is 2. Now the valence electrons of the magnesium will be taken as 2. So now the valence electrons of the magnesium is taken as 2. Now which block does this magnesium belongs to? As we have written the electronic configuration, we have S block at the last. Now this belongs to S block element. S block element. Now if we take an example for like oxygen. Oxygen atomic number is 8. And when you write the electronic configuration, we write it as 1s2, 2s2, 2p, as we have 4. So 1s2, 2s2, 2p, 4. Now this is the first orbit, which is called as the K shell, and this is the second orbit, which is called as the L shell. Now which is the last orbit over here, the outermost orbit? Yes, so L is the outermost orbit. So this whole thing we should consider. To find out the valency electrons, we should consider the whole thing over here, which is the L shell, which is the outermost orbit. And what is the number of electrons present in the outermost orbit or in this L shell? 2s2, 2p4, that is 2 plus 4. 2 plus 4 is equals to how much we get here? 6. Now the valency electrons of the oxygen is taken as 6. The same way also, when you write the electronic configuration, last orbit what you have, that should be considered as the valency electrons. And oxygen belongs to which block element, whether it is S block or P block or D block. See, when you write the electronic configuration, last you have p orbital. So as we have the p orbital, it belongs to the p block element. So now you got about what is meant by valency electrons. So it's nothing but the electrons which are present in the outermost orbit. Now coming to the valency. So valency is nothing but the combining capacity of the elements. So the combining capacity of the elements that varies from one element to another element. Like if we see here in this table, now when we take for the alkali metal family, so alkali metal family we have 1A which has the valence electrons as 1, 2A which has the valence electrons as 2. Why? Because NS2, that means 2 electrons we have. 3A, that is NS2 NP1, that is 2 plus 1, 3, that is we have 3 electrons. Coming to the carbon family, 4A, that is 2 plus 2, 4, so we have 4. Coming to the nitrogen family, 5A, that is 2 plus 3, 5 valence electrons. And 6A, 2 plus 4, yes, 6. At the same time, 7A, valency shell, 2 plus 5, 7. Noble gas, 8A, 2 plus 6, 8, so we get 8. Now coming to the valency for this is, for the first 4 groups, that is for valency 1, if the valency electrons are 1, then the valency is also 1. If the valency is 2, it is also 2. Valency is 3, it is also 3. If the valency is 4, it is also 4. But when coming to the valency 5, here it will be decreased, which is 5 minus 8 we get as minus 3, so we represent as 3, that is minus 3. Coming to 6 minus 8, minus 2. 7 minus 8, minus 1. 8 minus 8, 0. So how do we get these values that we'll be seeing in the chemical bonding? So we have a next episode of which we call the chemical bonding. In that chemical bonding, how do we represent this, how do we get these valencies, that will be explained in the next chapter, that is called the chemical bonding. So we have the valency electrons and we have the valency over here. Now if we see here, the valency is 0 for the noble gases. So the noble gases like helium, neon, argon, krypton and xenon. So all these noble gases, as they have the valency 0, they won't combine with any of the element. So they have a nature that which doesn't get combined. That is why they are called as the noble gas or the inert gas. Why? Because they won't get combined with any of the element, as their valency is 0. That means they don't have any combining capacity, so their valency is 0 here. So thank you everyone. So today we have discussed about the Mendeleev periodic table and we discussed about the modern periodic table. In next episode we'll be seeing how to find out the element in which period and in which group in a modern periodic table. So right now, thank you for your time. Please subscribe the channel and wait for the very new interesting videos. Thank you one and all.